everyone. So in this video we are going to see basics of AC circuits, or specifically a series of videos. And in the first video of this series I am going to talk about the basics of alternating current. So you see a question here. Let's try to read the question and then solve it. So an AC current has the frequency of 50 Hertz and a maximum value of 120 amperes. Write down the equation for the instantaneous value of the current. So we know that alternating currents are in the form of sinusoidal equation. So basically I can answer the question as this. So the current I, instantaneous value. So instantaneous values are typically given a small letter. So I of t, because it signifies instantaneous value, that means at every instant, which means if I substitute the value of t at that time, I'll get the I. It's like a expression. So 120 is the maximum value. So general equation is I max sine of 2 pi f t plus phi. So this is in amperes. So this phi is the phase. In the present form of the question, the phase information is not given. So I can consider phi as 0. Frequency is given as 50, 2 pi are constants, and I max is also given. So I of t will be equal to 120 sine 2 pi into 50. So this is all just product into t, and this is 0. So phi I am assuming 0. So that's it. I have the solution for the first. So if I substitute the value of t, I can get the value of I. So general observations from this, what you can see is, if I plot it in the form of a waveform, so this is time axis and this is the current axis. So this is the value of current. Then this particular equation will look something like this. So this is the alternating current, and it keeps going on like that. So what is the maximum value? So this is the maximum value that we are reaching. So this maximum value will be 120 amperes. And the question we can ask, how much time it takes to reach this maximum value. So for that, you look at the frequency. Frequency is 50 Hertz. That means in 1 second, there are 50 cycles. Cycle means a positive and a negative part. So this entire is a cycle. So this one is the time period. So this is 1 cycle. There is another cycle. Let me complete up to here is 2 cycles, 3 cycles, like that. In 50 seconds, I have, sorry, in 1 second, I have 50 cycles. So let's, so to get the time period, that is capital T, I just have to divide the frequency. So that is 1 by 50. So I get 20 milliseconds for that. So this value is 20 milliseconds. Therefore, this value, half of it is 10 millisecond, and further half of that will be 5 millisecond. So in 5 millisecond, it achieves the maximum value. In fact, you can verify this. If I substitute here 5, 10, 15 or whatever values, I keep getting the 0 and maximum and minimum values. So for example, if I substitute 10 here, so 0, 0 will like 50 into 10 milliseconds. So this entire thing will become, it's like a multiple of pi, and it becomes 0. Anyway, we're going to see that in the further questions. So let's continue. I have prepared series of questions. So if I go down, so this is the next question. Counting from the instant of current crossing 0 and becoming positive, determine the value of current after 5 millisecond, 7 millisecond and 18 millisecond. So let's look at that. So if I want to answer this question, so what is the value of current after 5 millisecond? So for this we need to use a calculator. We already have the equation. So this above equation, if I just simply substitute in this equation, if I simply substitute the value of t, I get it. And for doing this calculation, let me use the Octave interface. Octave or MATLAB or similar, the same syntax works on both. So let me write this equation in the Octave interface. I am just switching over to Octave interface. So here on the screen, you see the command window on the right side and the editor window on the left side. So we are not using editor for now. I'm directly using the command window. So let me enter the expression here. So what is the value of current? So I I'm using capital I as a variable. So 120 is the maximum value, sine, and then 2 into pi into frequency is 50 into 5 milliseconds. So that I'm using 5 to the power of, so 5 e minus 3. This is the notation, 5 raised to 10 to the power of minus 3. So just 5 milliseconds, and that's it. So if I just press enter, I get 120 amperes. So this is the answer to the first question. That means that's what we see here. At 5 milliseconds, I get 120 amperes of peak current. So at 5 milliseconds, the current is 120 amperes. So this is I of t. So specifically small I of t. Now the question is, what about the value at 7 milliseconds? So at 7 milliseconds, just I go back to my interface and then MATLAB interface, and here instead of 5, I use 7. That's it. So I'm getting 97.082 amperes. So I'll just 97.082 amperes. So at 5 milliseconds it was more, but after some time it is less. So as you can recall, this is increasing and then decreasing. So at this point it is 120. This is 5 milliseconds. So at 7 milliseconds it has reduced to 97.082. That's what we see here. Now what happens at 18 milliseconds? So you know at 10 milliseconds we are going to touch 0. So then we are going negative. And at 20 milliseconds we are going to again 0. So therefore at 18 milliseconds we expect something like a negative value. So let's come back here, and then I just change the value here, 18 millisecond. And as expected, I'm getting minus 70.5. So let me write that. So at 18 milliseconds, so I get minus 70.5 amperes. So meaning of this minus 70 is that the current is flowing in the reverse direction. So if you are considering the current measuring in a line like this, and if I notate this as my positive direction, then actually the 70.5 amperes are flowing in the backward direction. So that's about this question. Now, one interesting thing, let's see what happens at 12 milliseconds, although this is not. So what happens at 12 milliseconds? So again, we do the same thing. I go to my command interface, and instead of 18 milliseconds here, I substitute 12 milliseconds. So I'm getting minus 70.534. So if you notice, even if I give 18 millisecond, it is same, and even at 12 milliseconds, it is same. So this is exactly the same as minus 70.5 amperes. So you might get a doubt, although this is alternating current, how come it is same at this time? So if you look at the graph, then you will be able to understand. If you look at the waveform, so I just draw the negative cycle of the waveform. This is 15 milliseconds, and this is 10 milliseconds, and this is 20 milliseconds. So we know from this that at 15 milliseconds we get the maximum or the minimum, I should say, that is minus 120 amperes of current. So if I move 3 seconds on this side or 3 seconds on this side, it doesn't matter. It will be the same current. So if I just draw two lines, actually since it is not according to scale, it doesn't appear that way. But then yeah. So this value was 70.5 amperes with minus sign. So this is 18 millisecond and this is 12 millisecond. So that is the reason why you get the same values like this. So there is a minus 70.5 on before 15 millisecond, and there's a minus 70.5 after 15 milliseconds. That's what you see. Let's continue. Let's go to the third question. So the third question is like this. When does the current achieve a value of 84 amperes for the first time, for the second time, and the third time? So if I draw the waveform once again like this is a sinusoidal waveform. This is 120 and this is minus 120. So now 84 amperes will be somewhere, so this is my time axis, this is my current axis. So this is amperes. So 84 will be somewhere here, for example. So if I draw a straight line, This is the first time I am achieving the 84. This is the second time I am achieving 84. This is the third time I am achieving 84, and this is the fourth time. So at different times, I am getting this different value. So this is the question. So how to know this time? How to know this time is what we want to see now. So as you know, this is 10 millisecond. This is 20 milliseconds. So 20 millisecond, it covers one cycle. This is time in milliseconds. So I just want to rewrite the equation because I of t is I max sine 2 pi f. So let me use a pi symbol. 2 pi f t plus phi, but for our problem the phi is 0. The phase is not existing. So I want to know, here the t is known, t is unknown and I of t is known. So I just want to rearrange this. So by simple rearrangement, I'll just write 2 pi ft is nothing but I max divided by I of t. And therefore t is nothing but I max by I of t whole divided by 2 pi f. So using this formula, I can substitute the value of, this is I of t by I max. Let me just delete this. I of t divided by I max, and this also is I of t divided by I max. So let's feed this equation into our octave interface. So t equal to I of t. So the question I of t that is asked for is 84 amperes. So 84 divided by 120. This whole thing is being multiplied I have to use sine inverse, right? So I forgot sine inverse. So this will be sine of this. So this whole thing is wrong. Discard this. So this will be t equal to sine inverse of I of t divided by I max into 1 by 2 pi f. Okay, so let's do this. So here I'll write a sine. So a sine is the function which will do the inverse of sine, and divided by 2 into pi into 50. So this equation will tell me at what time I get the 84 amperes, and from this you can see 2.46 milliseconds. 0.00246, this is the seconds. So I get 2. So I'll round it off to 2.4 seconds, milliseconds. So at 2.4 milliseconds, I equal to 84 amperes for first time. Now the second time, unfortunately, again, if you write the same equation once again, you don't get the second time answer. So I want to choose this point. So since I know from here this distance is 2.4 milliseconds, I will subtract 2.4 milliseconds from 10. So this will be 10 minus 2.4 milliseconds. That is when I get this. So 84 amperes first time, second time, third time. So first time I got 2.4 milliseconds. Second time will be 10 minus 2.4. So let me do that. 10 minus 2.4 milliseconds. So I get 7.6 milliseconds. How about third time? So the third time it will be one full time period 20 milliseconds plus 2.4 milliseconds. So this will be 22.4 milliseconds. So just understanding the waveform, the value of current keeps changing like this. So this is time. So this, I think this is the solution for third. So I'll just put third answer. So let's continue. So I have one more question. In fact, I have two more questions. So what is the shortest time for the current to change from 40 amperes to minus 70 amperes? So that means, again, look at the waveform. So the current reaches 40 amperes. So somewhere here. So this is 40 amperes here and 40 amperes here. And minus 70 amperes is somewhere here. Minus 70 amperes and minus 70 amperes. So if I want to know what is the shortest time, that means I take the second 40 amperes here and the first 70 amperes here, and this time difference I want to find out. So this time difference is what I am interested in. So how do you do that? So if I call these points A, B and C, so AB I can find separately and BC I can find separately, and then I will add them, so I'll get what is this. So let me go back to my interface, and then so this first time when it is reaching 40 amperes, so I put 40 here, and this variable I call it AB, and next time when it is reaching, or when it is reaching minus 70 amperes, so this I'll say, this is strictly not AB, so I'll just keep it as T. So I'm getting something like this. So by the way, here I'm getting negative value for T, so which is again not the correct value, or it actually calculates the, when I do sine inverse, it actually calculates the least magnitude value of T. So let me explain what this is. So this is 1.98. So I'll round it off to minus 2 milliseconds. So when I do sine inverse 40 by 70 into 1 by 2 pi into 50. So this I am getting as, so 1.08 milliseconds. So I'll just round it off to 1 millisecond. Whereas sine inverse of minus 70 by, sorry, this is 120 into 1 by 2 pi f. So this one I am getting it as, so 1001985. So I can approximate to 2 milliseconds with a minus sign. But then the negative time is doesn't exist. So basically what it is doing is, so this is my 0. So on the negative side, how much time to reach minus 70? So is what it is calculating. So anyway, I can add these two quantities. So I'll be able to, so the distance between A to C is exactly same as the distance between this point to this point. So, or in other words, if I extend this, so this is plus 40 and this is minus this one. So this distance will be exactly same as the distance that we are trying to measure. So basically, just by observation, just by looking at it, so my answer is 3 milliseconds. So this is the answer for this. So the shortest time it takes for the current to change from 40 to minus 70 is 3 milliseconds. So this is slightly tricky unless you understand the variations, understand the sine wave and all these things. You will not be able to solve this. Just simple calculator will give you some cryptic numbers, but you should know that you have to disregard this minus and then add and all these things. I hope you understood this problem. So let's finally go to the last question. So if this current is flowing through a 5 ohm resistance, what is the instantaneous power at 5 millisecond, 10 millisecond and 17 millisecond? So resistance is 5 ohm. So basically this is the 5 ohm resistance and our current I of t is flowing at this. So what is the power? So power, instantaneous power is instantaneous. It's like I square into R. So power is instantaneous, current is instantaneous. So I just matter of uh, substitution. So time is 5 millisecond, 10 millisecond, and 17 millisecond as asked in the question. And the current at 5 millisecond it will be 120 amperes. We have already seen that. So at 10 millisecond it is 0 amperes. So again remember, so this is 20 millisecond is your total time period, and this is 10 millisecond it will be 0. At 5 millisecond half of that it will be plus 120 highest value. Now at 17 milliseconds I need to calculate. So let me just go back to my interface, and then I'll use this here in the place of 12 I substitute 17. So I'm getting minus 97 amperes, 97.082. So I ignore that and say minus 97 amperes by rounding off. So what is the power? So power is nothing but I square, I of t square into R. So it doesn't matter whether the current is going from left side to right side or right side to left side. Power is going to be consumed, heat is going to generate in these resistors. So it is always going to be positive. That is also because I is getting squared here. So 120 square into 5. So 0 square into 5, of course it is 0 watts. And here 97 square. So although minus is there, it becomes plus. So is how much? So let's do that. 120 square into 5. 72,000. So or this is 72,000 watts, or it is 72 kilowatts. And let's do it for minus 97. So this is 47045. So 47045 watts. So this is positive, or 47.045 kilowatts. So I'm just converting to convenient unit kilowatts. So I hope in this short series of questions you found something about how to deal with a sinusoidal waveform. We will see more such examples in future videos. See you.